Hello everyone! Today is December 8th and we are ready to open a new problem from LeetCode for our Coding Advent Calendar. Today's problem is about binary trees as yesterday, but it is more interesting in implementation. Let's check this out. Okay, here is it. Leaf similar trees. Consider all the leaves of a binary tree from left to right order. The values of those leaves from the leaf value sequence. Here is a tree and here is the leaf level. For example, in a given tree above, the leaf value sequence is 6, 7, 4, 9, 8. Two binary trees are considered leaf similar if their leaf value sequence is the same. Return true if and only if the two given trees with the head nodes root 1 and root 2 are leaf similar. For example, these two different trees, they obviously different, but they have the same sequence of leaf level, leaf nodes, 6, 7, 4, 9, 8. Okay, we need to return true. For these two, we need to return false, because for the first one, the leaf sequence is 2, 3, and for the second one, 3, 2. Okay, so how are we going to solve this problem? The idea here is we can divide it into few parts. First, we need to write a function which will give us the sequence of leaf values from a given tree. We have two different trees, so we can call this function twice, get sequence of leaves and compare them together. So for example, we get two different arrays with leaf values. And second part of our algorithm is comparison of those two arrays. But we can actually do a little bit better. We can stream these two sequences. What does it mean? We don't actually have to calculate all of them in order to compare them. We just need to sequentially compare values one by one. If we have any difference, then we can consider these trees as non-leaf similar, right? So in this case, if first node of the trees are different in one case and another, we can immediately return false, and we don't have to traversal the whole tree. So how are we going to get this sequence of leaf nodes? We need to traverse the tree, and there are a few canonical ways to traverse the tree. For our case, we can use Postorder traversal mechanism. That means we read nodes from left to right. So left, right, then top. Left, right, top. So for this case, we will get 6, 7, 4, 2, 5, 9, 8, 1, 3. So we go deep to left, then to right, to left, to right, up, up, to right, to left, to right, up, up. You got the idea, right? So let's do this. Let's start coding. So what are we going to do? So first we need to get these two streams. Okay, here I call the function which is not yet implemented, and I think that this function will return streamed sequence. So it is a sequence which has lazy evaluation. So we don't have to evaluate it immediately. We can evaluate it one by one. And in order to get this kind of sequence, we are going to use enumerable, or more precisely for our case, we are going to use enumerators, because we need to have full control over how are we taking these values. Okay, in order to be able to call this function getEnumerator, we need to pass enumerable to it. This is .NET C# stuff, guys. For your programming language, there should be something similar. I guess you will find equivalent. Enumerable of something okay, enumerable of something. And now what are we going to do? We will we have two enumerators, and we do move positions in these enumerators synchronously forward. So and we are going to do this until the end of these sequences. So we need to somehow understand that this is the end of the sequence, and the implementation of enumerator, once it reaches the end, is this. There is a specific. If you call current of the end of enumerator, it will throw exception because we reached the end and cannot read the value from it. We read all the values. So for this case, I will do one little trick here. I will return combined value, which is value from the node, and I will also mark last node. So I will literally generate one more value, which will have some default value here, like 0, but it will be marked as last one. So I will not count it when I do comparison of these sequences, but I will be able to read the current value of this position from the enumerator without having to catch exception, right? So we do this movement until and until we reach the end of any of these sequences. If we reached, then we cannot move forward and we need to stop. And once we have the end of one of these sequences, we need to do additional comparison. For example, we need to check if one of these sequences is finished and another is not, and that means that one sequence is longer than another, and that means that leaf sequence is different in one from another. So, and we also need to check that values from these two currents are equal. If they are not equal, we also need to stop doing this and return something. Okay? So once we stopped here, we need to do the following. We have only one case in which these sequences are the same. If we were able to go through all elements in each sequence and we reached the end of each sequence, right? So only in this case these two sequences are the same. So if we reached the current last element of first sequence, and if we reached the end of the second sequence, only in this case we can return true. In any other case we have to return false. For example, if we reached the end of first sequence and we are not reached the end of second sequence, and vice versa, and also if we were if we kicked off this loop by this comparison, if values at some point are different, then we are not able to reach the end of any sequence because we stop moving these enumerators forward. So this part of algorithm is implemented, and now we need to implement this one. So how are we going to do this? Well, as I said, we need to implement post-order traversal algorithm of like traversaling the tree. And we need to do additional thing. We need to return additional value in the end of this sequence. So let's do it. So we will do post-order traversal, and we will return the value like this. So if we read the value from our post-order traversal mechanism, we will return its value and the value force for the last mark. Once we done reading this sequence, we need to also return additional value, which is 0 and true. And this true will be a marker. It will be one additional node in our sequence, which just means that we finished reading it. So all we need to do right now is to implement this function. Okay, how are we going to do this? So, as I said, we should implement canonical post-order traversal algorithm. That means we need to go to the left, go to the right, and then return the root of this current subtree, and do this in a recursive manner. So we will do it like this. If root left not null, then we need to stream recursive subtree of the left. So for this case, when we have root 3, we need to stream all leaf levels from left subtree, then stream it from right subtree and go up. So we will do a recursion here. Okay, it is from lowercase, and for each of these elements we need to yield it. Okay, once we're done, we also need to do this for the right part of the tree, right? Okay. And we actually need to implement mechanism which yields node values from the bottom of the tree. For example, if we reach the value 6 here, we need to consider it as a leaf level because it doesn't have any lefts and any rights, so we need to return it actually, so it will be able to go up in our recursion stack and pop up here. So if root left equal to null and root right equal to null, we need to return it. Okay, that's it. So I think our mechanism is implemented. So what we have here, we have post-order traversal mechanism which is able, okay, it should be like this, which is able to stream nodes from any tree, right? And only those nodes we actually interested in. We have mechanism which yields additional value in the end of sequence which is marked as false in order for us to be able to compare it appropriately. Let's do this. Okay. Yeah. Okay, something is wrong. I did something wrong. Let's do a quick check. Oh, I think exception. So I think the problem is here. Yeah. So it should be not true. So it should be false, right? Yeah. So we need to go through this sequence until we while this last is equals to false. Okay, so case 1, case 2, submit. Okay, our algorithm is accepted. That's it. So let's quickly try to estimate the complexity of our algorithm. From CPU consumption, it is obviously big of n because we need to go through the nodes. In worst case scenario, like in positive scenario, these trees are equal. That means we need to go through all leaves in both trees. So it's big of n because we need to check every node in both trees, but not more than that. From memory perspective, what do we have? In previous video I told you that it is big of n, but actually if you were careful enough and you were able to identify my mistake, we actually have big O of log n, which is the depth of tree, because we have as many stack frames which consumes memory as deep is our deepest tree. So it's big of log n because like logarithm on base 2 because we have binary tree. And I guess that's it. Wow, it took a little bit more time to implement than yesterday. But you should agree that the more effort you put into a solution, the more joy you get when the work is done the right way. Let's wait until tomorrow to see what the next problem is. Maybe it's about graphs or multi-dimensional arrays. See you tomorrow.